Hello everyone. In this video lecture session, let's have an overview about floods. First of all, the term floods, we are hearing this in a very extreme level position of the water bodies, which is occurring in a high level. That means the extreme harmful conditions, the term floods will happening. But here what is the purpose of engineering hydrology subject to having this flood as a concept? Because for designing any dam related structures, we have to identify the flood probable level, in an impact level, and in a high risk pattern level. So for that purpose, overview about the floods is very important, as well as the design of the floods. So let's have a look about the floods and about the design in a detail in the upcoming slides. First of all, floods. Technically speaking, the usual definition is not at all happening. So the first line indicates unusual high stage of a river. As I already said, extreme level in a water body which leads to flood. So here technically the definition was mentioned, it is not in a usual level, it is in an unusual high stage of a river due to runoff from the rainfall or melting of snow. Because floods will be happening in a river basis as well as in dam structures when the overflow of the dams, wherever the water bodies which attains a normal level position and the extreme levels will be happening, this flood will occur. So that's what they are indicating. A flood is an unusual high stage of a river due to runoff from rainfall or melting of snow in quantities, that too confined in a normal water surface. So unusually high stage of the river, which I already mentioned, the extreme level. Look at the diagram, just a understanding purpose diagram. In a building, 100-year flood level, rivers are drained, that is also mentioned. But high stage of the river due to the runoff from the rainfall as well as melting of the snow in quantities. But in normal water surface, elevation of the river is also matter. That is resulting the unusual meteorological combination. Because sometimes continuously the rainfall will be there in major metropolitan cities. We are getting more rains. That is also leads to the floods in our roadways everywhere. But some conditions, dams will be overfilling and unusual high stage of the river due to runoff. So everything is happening. So floods, keeping in mind, technically speaking, floods is an unusual high stage of a river due to the runoff from a rainfall and or melting of snow in quantities too great to be confined, as well as normal water surface elevations of the river or the stream, which is resulting to unusual meteorological combination. Here comes the design of flood. First of all, the flood, in the point of view we are speaking unusual or extreme harmful effects, everything and all. So designing of the flood, we have to analyze the past factor as well as the future factor as well as the current scenario, how the maximum flood of any structure can safely pass. That is known as design flood. Look at the first line. The maximum flood that any structure can safely pass is called design flood. That means it is selected after consideration of economic as well as hydrological factor. Because by identifying this design flood, we can able to design any dam structures or any other water structures, hydroelectric power projects, everything depending upon this design peak analysis of the flood. So finally, the maximum flood that any structure can safely pass in the design flood by considering the hydrological factors, and after the consideration of economic factor also, then it is related to the project future. As I already said, for example, the spillway design flood, which may be higher than the flood control design flood, or the design flood adopted. So look at the figure having 100-year flood plan, the base flood, the flood fringe, the floodway. How about the stream as well as the flood fringe nearby the house, the mountainous level, the upstream as well as the low stream. So by considering this this picture in mind, we have to analyze the design flood adapted for the temporary coffer dam as well as the flood controlled reservoirs, the design flood which is related to the overall project future. So design flood is a major role for calculating these types of the analytical observations as well as the variations in determining the risk factors by considering the impacts. In this slide, the design flood overview by considering the cost of the structure to provide flood control and the flood control benefits, how it is categorized direct as well as indirect. In a direct level, prevention of damage to the structure downstream, disruption communication, loss of life, property, damage to the crops and underutilization of the land. So these are all the direct thing. But in indirect, the money saved under insurance and workman compensation loss, higher yields from intensive cultivation of protected lands and elimination of the losses arising from the interruption of business, reduction in diseases resulting from the inundation of the flood waters. So design flood is selected by considering the cost of the structure, because directly as well as indirectly, when the structure is designed for a flood less than the maximum probable, there exists a certain amount of the flood risk. So by considering the flood risk of the structure, it is economically to design 100% flood protection. So protection plays an important role. Obviously everyone know how about we are protective in the structure. That's why the civil engineering field applications as well as the structural applications, everything will vary, everything will matters. So here the direct as well as indirect in an economical way as well as technical way, in the structural point of view also, we have to give the design of the 100% flood protection. Here comes the standard project flood, maximum project flood and the design flood. First of all, the standard project flood. This is the estimate of the flood likely to occur from most severe combination of the meteorological and hydrological conditions, which are reasonably characteristics of the drainage basin being considered but excluding extremely. Because standard project flood is a estimation of the flood, because severe combination, because we can't control the nature, which I already said, meteorological conditions as well as the hydrological condition. First of all, we have to analyze the standard project flood, how the ranges will be, which are reasonably characteristics of the drainage basin. It is being considered but excludingly extreme rare combination of this project flood. By considering the major pattern, the design of the flood is possible. Then here comes very important pattern, that is maximum probable flood. Without this, nothing risk identification, no impact determination will be happening, because this differs from the SPF in that it includes the extremely rare and catastrophic floods and is usually confined to spillway design for higher dams, because this standard project flood is usually around 80% of MPF, that is maximum probable flood for the basin. So very important, maximum probable flood, which is differing from the standard project flood, because here we are analyzing how much amount of the extreme ranges maximum probable flood will be happening. Then finally comes the design flood. By considering the above two process, that is standard project flood as well as the maximum probable flood, we are designing the design flood, that is, it is the flood adopted for the design of the hydraulic structure. Here comes the spillways, bridge openings, flood banks and extra other hydraulic and then water structures, water body structures. So these are all the things very important we have to consider in mind. Standard project flood, maximum probable flood. By happening this consideration, we are going to design the hydraulic structures like spillways, bridge openings and flood banks. Here comes the estimation of the peak flood. Maximum flood discharge, that is peak flood in a river, may be determined by these are all the following methods, like numerical calculations, empirical formula and curves, concentration time method, overland flow hydrograph, rational and unit hydrograph method. Why I have highlighted these two methods? Because these are all the basic fundamental and very important flood frequency studies. These are all the things we are going to estimate the peak flood. Estimation of the peak flood. Physical identifications of past floods, flood marks, and the local enquiry by considering a case study pattern or any other regional wise pattern. How about the flood level? How it is extremely happening, as well as how the ranges are high and the flood fringe. And by noting these are all the flood marks by a general local enquiry or any surveying field level investigation, how much amount the depth, subfluxes, and heading up of the water near bridge openings or similar obstructions and other items actually at an existing bridge on weir in the vicinity. The maximum flood discharge may be estimated by the use of Chesney equation or Manning's equation. Let's have a look about this empirical formula. Look at here, there are plenty of empirical formula, but we are focusing Q equal to 412 a power 3 by 4, and Higgins formula Q equal to CD, that is coefficient of discharge, a power 3 by 4, and reverse formula Young's formula. These are all the formulas for the identification of the peak flood, where Q is the peak flood and A is the area of discharge, area of drainage basin, CD and Higgins constant and Reeves constant. Estimation of peak floods, here it was mentioned in the graphs how much amount of the catchment area depending upon that maximum flood drainage. Areas having similar topographical features and climatic conditions they are grouped together. All the available data regarding discharges and flood formulae are compiled along with their respective catchment area. So by considering this catchment area, we are attaining the maximum flood discharge per cubic meter per second, because these envelope curves are mentioned in the graphical pattern for the estimation of the peak flood. Here comes another method, that is the rational method. This rational method is most effective in urban areas with the drainage areas of less than 200 acres. The method is typically used to determine size of the storm sewers, channels and other drainage structures. The rational method is based on the application of the formula, that is Q equal to KCIA, where C is the coefficient depending on the runoff qualities of the catchment, that is called runoff coefficient, which ranges from 0.2 to 0.8, where A is the area of catchment and I is the rainfall intensity, K is the conversion factor. For English units they are mentioning that's the fundamental, like K factor they are mentioning as a unit 1.008 to give flows, and for SI units they are mentioning K equal to 0.00278. For while doing calculations in rational method, these are the units can be used. So we have to keep in mind the rational method for based on the application of the basic formula Q equal to KCIA. Here comes the rational method continuation by plotting the graph depending upon the intensity as well as the duration. I is the equal to the designed intensity or critical intensity of the rainfall corresponding to the time of concentration at the recurrence interval. IC can be found from the intensity duration curves. Typical intensity duration curves was highlighted in the graphs. Depending upon this duration as well as the intensity along with the time period T for 25 years, 50 years, 100 years, depending upon the time period, the estimation of peak floods is happening with the help of this rational method. Estimation of peak flood in rational method in another parameter by considering the type of the terrain. Look at the tabular form. Flat residential areas, the value of C 0.4, 0.6, 0.8, and depending upon this value of C, that is the time of concentration. Here comes the intensity, duration, frequency curves. These are not at all available for the catchment, but maximum precipitation occurs during the storm period, that is TR. The time period here attaining is very important because the time of concentration depending upon the type of the terrain, that is flat residential area, moderately steep residential area, built up areas, rolling hands, hilly areas and flat cultivated lands and sandy soil. Here comes the time of concentration. It is defined as the time needed for the water to flow from the most remote point in a watershed to the watershed outlet. The time of concentration equals the summation of the travel times. That means TC, that is equal to L by V, that is 1, and then L by V 2, 3. It is continuously, it keeps on going. Depending upon the time of concentration, the hydraulic length is determined. That is the distance between the most distant point in the watershed and the watershed outlet. So by considering inlet as well as the outlet, depending upon the time of concentration, how much amount the time needed for the water to the flow and the most remote in the watershed, we are considering the time of concentration as well as the hydraulic length by considering the distance between the distance point in the watershed as well as the watershed outlet for this estimation of the peak flood. Here comes one of the formula, Kirchhoff formula, T is equal to 0.0078, L power 0.77, S power 0.385, where Tc is the time of concentration in minutes, L is the maximum length of the flow, S the watershed gradient or the difference in elevation from the outlet. For using the elevation point as well as outlet and the most remote point divided by the length, by considering this formula, we are determining the estimation of the peak flood. Here comes one example problem for an area of 20 hectares of 20 minutes concentration time. Determine the peak discharge corresponding to a storm of 25-year recurrence interval. For example, T equal to 25-year, that small t 20 minutes. Here comes the formula Q equal to KCIA, which I already said. This is the basic formula. So applying KCIA values, and we are finding that Q by using this rational method. And here comes one more example for a culvert project in the foothills of the Alberta, Canada. Here they are taken as a case study. So determining the peak flow by using the rational formula, return period for the design, that is for 50 years. Step 1, calculating the drainage area, marking the drainage area with the help of this Google map. They are calculated drainage area of was 8 kilometers, that is 800 hectares. And in the next two, they are determining the runoff coefficient. Area may be composed of different surface characteristics. So we have to determine average value of coefficient C, that is 10%, 90%, once again 0.1 into 0.8, 0.9 into 0.4. Finally, the drainage basin, they are considering the coefficient, runoff coefficient, that is 0.44. This is the step 2, determining the runoff coefficient. In the step 3, they are determining the time of concentration by using the Kirchhoff formula. T is equal to 0.00032, L power 0.77, S power minus 0.385, where L is the maximum length of the water travel, that is 12,000 meter, S surface slope, H by L, that is 0.108, and H difference in elevation between most remote point and the outlet. The time of concentration, that is 1.04 hours. So by considering this, we are determining the time of concentration. Finally, we are identifying the rainfall intensity with the help of the graphs, the short duration rainfall intensity and I equal to 30 mm per hour, and the intensity level depending upon the case study area of the Canada. We are considering the various factor and the rainfall intensity is determined. Here comes the final step, the calculate of flood peak discharge with the help of the Q equal to 0.00278 CIA metric, and finally the answer obtained is 29.5 meter cube per second. Finally, this is a download section of NPTEL animation as well as ebooks. Those who are having any other issues related to these concepts of any other calculations, you can go through the NPTEL links as well as animations as well as the engineering hydrology textbook by K. Subramania. Those who are having any doubts, you can have a go through on these things. Thank you everyone for your patience listening. Thank you so much.